Okay, good morning, everybody. The last 2 days we did all the hard groundwork, and now today we can actually start doing interesting things with the tools and techniques we've developed the last two days. Let me recap first where we are in terms of the tools we have. So we talked about series approximations, where we're expanding functions in terms of basis functions. And the basis functions could be Fourier. We looked at Fourier series, and we looked at Chebyshev. And what I'm writing down, pretty much one-to-one, also applies to the Legendre polynomials that Joffre is using in spectra. With each set of basis functions, there comes a special set of associated grid points. Xi, I goes from 0 to n-1. As many grid points as you have basis functions. And then we showed that we have various really nice matrix multiplications available to do the hard work for us. If we have U at the grid points, we can get the spectral coefficients by one matrix multiplication. If we have the grid point values, we get the spectral coefficients. If we have the spectral coefficients, we can get back the grid point values. P I k U tilde k. And this is a sum over I. And perhaps the most interesting of them all, we have also shown how to go from the grid point values directly to the grid point values for the derivative. So there's another magic matrix that gives us the derivative at the grid points as a sum over the grid point values itself. And the really nice thing in all of this is that all of this works with astounding accuracy if you're using the right grid points and if you have smooth functions you are working with. Highly accurate for smooth functions, plus correct grid points. And of course, a fourth thing we can also do is we can evaluate our series at any point we want. At the grid point, it's nice. You just do the matrices. Anywhere else, well, you have to go back to your defining equation and really sum up your basis functions. But because we know the basis functions, we can do this. Okay, 2 days ago, you did this for Fourier series, and yesterday in the tutorial, the task was to repeat all of this for Chebyshev. And let me see, this is very small. And so over the course yesterday, you developed basically this nice little helper function, Chebyshev helper, that returns the grid points for a given expansion order n, and it returns all the various useful matrices. The two spectral, two physical, the first derivative matrix, and the second derivative matrix, which is just this one multiplied with itself. By the way, how did you find these problems? Were they easy? Were they hard? Were they fun? I should use Joffre's cards. And so here's one of the examples from the problem set. We're starting out with u equals x squared. The x is already the magic Chebyshev grid, because these are the Chebyshev points that come back from our nice function. X squared, and what I'm doing here first is I'm taking my function, multiply by the S matrix, multiply by the P matrix, and what I should find back then is the same x squared I started out with. And hopefully this is visible in the plot below. Yep, that's this line here, which is x squared. The next thing that's going on is I'm multiplying u by the first derivative matrix. This funny add symbol is Python's way of doing a matrix multiplication. And again, what comes back is a straight line. The derivative of x squared is 2x, and it very much looks like it. And the green line is computing the second derivative that just gives you a straight line at 2. So all of this looks like you think it should be looking. And if you're not familiar with the compact NumPy notation, one could also do this the hard way. Initialize a new variable for the derivative, and now loop around to your heart's content to sum up this matrix multiplication by hand. And then we can plot this again. And no big surprise, what you find is that the matrix multiplication by hand gives you the same result as the more compact NumPy matrix multiplication. But I should warn you that whenever there are operations in your programming language of choice that take a lot of data at once and do all of the work inside, those functions are always quicker than anything you can write out by hand. I haven't timed this, but I would expect that for large n, this handwritten version might be a factor 10 or a factor 100 slower than this one up there. Whenever you have the chance, use built-in functions that operate on as much data at once as you can. And whenever possible, avoid explicit loops, because explicit loops are really difficult to optimize for the compiler. Whereas here the compiler and Python knows from ahead of time, the user wants to do a matrix multiplication. So I have my highly optimized routine for that and will give him an answer or her an answer very, very quickly. Just for illustration purposes, here's again our u that we have initialized with x squared. If I'm computing the spectral coefficients from it, I get back a 0.5, 0.5, and all zeros. So x squared is equal to 0.5 times the 0th Chebyshev polynomial plus 0.5 times the second Chebyshev polynomial and nothing else. The second Chebyshev polynomial is 1/2 x squared, no, 2x squared plus something else. So this 0.5 cancels the 2 in the 2x squared to give you the 1x squared we had up in the function. Taking the derivative turns these two numbers magically into the 2 here, which is the 2x. T1 is just x, so this is the 2x representation. And the second derivative is just a 2 in the 0th polynomial. And so you see how all of this works out. And with the recurrence relation that we talked about yesterday and that you coded last afternoon, that are the magic things that take the numbers up here and put them then down into the lower lines. Here, not particularly interesting because you only have three relevant values to work with, but still. So this is how this goes. Any questions? As always, speak up whenever you have questions. Then let's move on and actually talk about partial differential equations and well, 3 or 4 types of partial differential equations that exist. Because we first need to know what their general characteristics are, so we know what type of solution scheme to apply to them. So the first type of equation are elliptic equations. Those are boundary value problems where you have some domain omega and you're solving inside this omega. So you're solving for u of x in omega. That might be a line. In our case, it's always a line. It might be a square, a circle, or it might be the entirety of R3, the full space we have. And typical equations here equations of elliptic character are potential equations of various potentials. So often written like this, a Laplace operator on the left, 4 pi rho on the right. You can use this for the gravitational potential or the electric potential. It's both the same equation. Or another example that showed up in last week in Thomas's course is the Hamiltonian constraint, which in some simplified version can be written like this. So this is the Hamiltonian constraint of GR. And you can see elliptic equations can be linear, like the first one, you only have a del squared u. They can be nonlinear. Here's a psi to the -7 next to the del squared psi. It's all pretty much the same. And what we need is we want to solve inside some region of space, no time here. And we need boundary conditions on the entire boundary. So all the way around, we need to put, for a single equation, we're going to need to put one boundary condition. We can either say that u is 0, or we can put a condition on the derivative of u, something like that. Either one works. The second important set of equations are one that Geoffrey already talked about yesterday. And those are hyperbolic equations, evolutionary equations where you start with data at one point in time, and you then evolve it forward in time. So let me first put down the sketch. So here, the idea is you have space and you have time, and you start with, you have some area in space, and then you evolve it forward in time, and you're going to find a function of u, function of space and time. The prototypical equation here is the one that Geoffrey has already put up. namely that the second time derivative of a certain function, I tend to call it psi, he called it g, minus the second spatial derivatives of the same function equals, well, 0 or a source, doesn't really matter. So that is a scalar wave equation, or just a wave equation. And as you've already learned, is that in many cases, Einstein's equations also reduce to this type of equations: second time derivative minus spatial Laplacian. Whether or not there is a right-hand side doesn't really change the character of the equation. Geoffrey already alluded to this. The character of a partial differential equation is determined by the structure of the highest derivative terms. And in fact, the difference between elliptic and hyperbolic is that if you write this thing here out as delta ij times ti dj, and if you write out this operator down here as a dd square, as a dt squared minus delta ij di dj, which is the same as the space-time metric eta ab times dA dB. The difference is that up here, all the second order derivatives are put down with plus signs, whereas here you have three derivatives of one sign and one of the opposite sign. And the one that goes with the opposite sign, that's the time direction that makes the hyperbolic systems different from the elliptic systems. So the typical example for hyperbolic equations is the wave equation. And the type of boundary information and starting out information you need for hyperbolic equations is also quite different from the elliptic equations. So here we need the following information. We need down here at time equals 0 in initial data. So we need to specify psi of x comma 0 is some initial function, let's call it g of x. And we need to specify psi dot of x comma 0 is some other initial function, fg, let's call it, I don't know, g1 and g2 of x. Then next, along the time-like boundaries over here, on the time-like boundaries, we need to specify boundary conditions for some of the variables. Not all, usually more than 0, but some. Boundary conditions on some variables. And the curious thing even down here is I have one wave equation for one variable psi here, but I still need two initial value conditions on psi and on psi dot. And this is because this is a second order equation in time. And finally, at the end, up here, at t final, we have no conditions at all. So the system here is highly different from the elliptic equation. For elliptic equations, you have one boundary conditions all the way around. This one down here. This is just a symbol for the spatial domain. So omega is the set of x values which are inside the computational domain we are solving for. Same omega as up here. It's an omega is a part of a subset of Rn. For our purposes, usually just the real line, but in many other problems are free because we have three spatial dimensions. So those two things are fundamentally different. Here we need one boundary condition per variable all around. Here we have some parts of the boundary of the space-time volume where we have many boundary conditions, some where we have none, and others where we have some, and the number that we have to pose over here might actually change during the evolution as well, if the situation is complicated enough. And all of this boils down to the fact that hyperbolic systems are, of course, evolutionary, and the future determines the past. And so you have to specify things in the past, but you're not allowed to say what happens, what's the outcome at the future, because you're actually evolving there, and the equations are telling you that. Another point about hyperbolic equations is that they have finite propagation speeds. So any information is only traveling with a finite speed. And with the finite propagation speed comes the concept of domain of dependence. So for instance, if I have a point here in the volume, in space-time volume, it will only be affected by whatever happens in the past light cone or propagation speed cone of whatever is the fastest propagation speed in the hyperbolic system. For all the ones we deal with in general relativity, we usually want to have this fastest propagation speed to be the speed of light. And in many cases, all propagation speeds are the speed of light, simply because this is the speed with which gravity, photons, and so forth propagate through space. The third type of system, which I'm not really much talking about, but let me just put it up for completeness, are parabolic systems. So the situation is the same as for hyperbolic ones. You have this type of setup. You need initial conditions down here, and you need boundary conditions. And the typical hyperbolic equation has a first time derivative, say t by dt of t, and then it has still a spatial second order derivative, like a Laplacian. And these type of equations are diffusion equations, where you have some type of diffusion coefficient sitting here. And for instance, if you consider T to be the temperature in a material, then the temperature within the material will roughly behave according to this line, that the higher the curvature of the temperature gradient is, the more quickly the temperature changes at that particular point in the material. The One difference between here and the hyperbolic systems is that diffusion equations, parabolic systems, have infinite propagation speeds. And that makes them not really suitable or useful for general relativity, where we always have light cones. They also need quite different numerical methods to deal with these infinite propagation speeds. So we will not cover them here in class. So these are the three typical cases of partial differential equations that are often talked about. But it turns out there's a fourth set, which is also closely related and which can be addressed very nicely as well with spectral methods. And so I'll be lumping it into this set of classifications of partial differential equation. And this fourth set are eigenmode problems. Eigenmode, eigenvalue. I'm using both terms interchangeably. And by the way, that reminds me, my lecture notes have just been updated in the Google folder. So everything I'm putting on the Blackboard today, as well as a few more pages of text I was talking about yesterday, should now also be available to you as well. So these eigenmode problems, for instance, arise for oscillations of a string. They also arise, for instance, when you do quasi-normal modes. Modes of stars or black holes. So let's talk about the string, because it's a much simpler system than the black holes. We take a string. Here's our string. And we log it along the x-axis at distance minus L and distance plus L. And now we ask the question, what's going to happen to the string if you plug it and it happily oscillates around? So if we start with defining a displacement of our string, I should have made it a little bit more displaced, so I can actually put in my displacement. So here's my h, for instance. Then what you will start out with is an equation like mu h double dot. I'm going to write down just Newton's force equation, is equal to T times H prime. So let's try to make sense of this. Mu is the linear mass density. So what's on the left-hand side here, this is units of kilograms per meter. What's on the left-hand side here is acceleration times mass for a small element of the string. And on the right-hand side, we have the string tension. If I can't read my writing, then you can't either. That is given in newtons times the curvature of the string. So the more tension you have on the string and the more strongly it is curved, the more it will try to come down again in the opposite direction, and it will accelerate the string itself. So that's the origin of that equation. And of course, because we are locking our string at the left and the right-hand side, we have boundary conditions that h of L is h of minus L equals 0. In order to get to this so far is a hyperbolic equation. So this is again the wave equation, second time derivative. If I move this term onto the left-hand side, minus second spatial derivatives, this is precisely the form down here. So far this is just a wave equation, and we could actually also solve the string and traveling modes on the string as a wave equation. In order to get to the eigenmodes, what we are doing is we assume a certain time dependence. We assume that h of t comma x is the same as a exponential e to the I omega t times a function of x only. And we have back our nice little u as always. If you now take this and substitute it into the string evolution equation, what we find is that the second time derivative turns into a minus omega squared because of the e to the I omega t. And now we still have the u of x. And on the right-hand side, we have t times e to the I omega t times the second spatial derivative, and that only operates on the u, is equal to t times u double prime of x. We can make this equation a little bit nicer if we want by redefining variables. So we can define a capital X that is in units of L instead of, so that the capital X goes from -1 to 1. And then we can also redefine, if I do this, then the right-hand side here picks up a 1 over L squared. So we have a T over L squared du of x dx squared, d squared u dx squared. And we can now also combine all the variables, all the coefficients we still have floating around here into one. So we can define capital omega equals, let me see if I can get this straight. This is little omega times, I have a mu on the left-hand side. I'm dividing by the t from the right-hand side. And I multiply with L. And if I do this as well, then the equation turns into, finally, a d squared u of x dx squared equals minus omega squared u of x. And so this combination here that shows up in the redefinition of omega, t over mu square root is the velocity of the wave along the string. L is its length. So this is basically the frequency in units of the travel time along the string. So just explaining all the variables. And what we now have down here is we have an equation. It still has derivatives. That's why I'm calling it partial differential equation. But now the two unknowns at the same time is the function u of x. We want to know the profile of our string when it's oscillating. And also unknown is the frequency omega, with which the string is going to oscillate. And that's why this is called an eigenvalue problem. We want to find a certain function, but it will solve the equation here only for certain values of the omega, of the eigenvalue. So we solve for u of x and omega simultaneously. Okay, so that's the type of equations we want to think about in the rest of the lectures and the rest of the week. The plan for today is to do elliptic equations. And it turns out the eigenvalue equations are very closely related to the elliptic ones. And so we'll also go to the eigenvalue equations. And then tomorrow and Friday, we'll be talking about the hyperbolic equations, where we have two new features to contend with. We have to deal with time. So tomorrow we'll figure out how to do time. First with periodic boundary conditions. So we don't have to worry about these vertical orange lines just yet and what to do there. And then later on Friday, we'll do the wave equation on a domain with boundaries. And so we have to think about how to do boundary conditions and what this sum variables here actually means on which we have to pose boundary conditions. Let me take a sip and see whether we have any questions.
Do we introduce the capital X variable like make it dimensionless? Like capital X is dimensionless, or like is there any specific purpose for you?
I introduced the capital X here for two reasons. Reasons 1 and 1.5 to make it dimensionless, the capital X. And to get rid of any unknowns and any constants in our final differential equation here. I could also have just kept this equation over here and have specified for you values for mu, t, and l, and then it's completely equivalent. And the other thing I'm doing here implicitly, I have set up the capital X such that the capital X ranges from -1 to 1, which you should recognize as the natural interval for Chebyshev polynomials. So by taking out the L here, I'm now back to the Chebyshev interval, and I don't have to worry about mapping the interval from something to someplace else. This makes my presentation here in class a little bit simpler. As part of the problem set yesterday, you were also asked to work in how you can remap the Chebyshevs to different intervals. And if we had used this remapping code, then, well, we could have stayed with -L to L, or we could also have gone from 0 to L directly. All of this is possible. It doesn't really change any of the underlying spectral mechanics. At some point, you need to go back to -1 to 1. I did it here on the analytical side before invoking the spectral methods, but you can also do it as part of the numerics. Okay, let's do an elliptic equation and see where this gets us. And why don't we come back to the problem we started out with on Monday morning?
Quick question. Are these classifications exhaustive? Are there partial differential equations that come up in physics that are neither of these four?
The question here is whether this classification is exhaustive. And the short answer is no, not at all, not in the least. But these are the four sets of equations where existence of solutions, well-posedness of equations and such can be established very easily. And you can write down many other types of equations, and almost all of them will just not be very useful, will not make sense in the sense that they may have multiple solutions or none at all and so forth. But for all intents and purposes, elliptic and hyperbolic are by far the overwhelming set of equations you will encounter. Sometimes parabolic systems, if you're going somewhat further away from fundamental physics and more into applied physics, because parabolic systems have the infinite propagation speed, they show up also. So in order to get there, you need to make some idealization, like what's going on in the diffusion equations. Parabolic systems also show up in Navier-Stokes. If you take a certain limit of Navier-Stokes, you get a pressure equation that also is parabolic in nature. And eigenvalue problems, yes, they also appear in many cases. Eigenmodes of anything that rings, stars, black holes, belts, you name it. So elliptic and hyperbolic are 90%. And eigenvalue problems and parabolic equations are also relevant, but on a much smaller scale. And beyond, I've never encountered equations beyond, I have to admit, except in mathematics textbooks, where all weird things are defined, including fractional derivatives and things like that. But we're not going there. We keep only integer derivatives. So let's actually solve numerical solutions of elliptic PDEs. And as I said, let's go back to our example from the first class. Q tuple prime minus x to the 6 plus 3x squared u equals 0 on x from -1 to 1. This is from the Boyd's book. I didn't choose this -1 to 1, but again, it's quite useful and neat. And we had as boundary conditions that at both ends, the function is supposed to be 1. Okay, so we have boundaries. And because we have boundaries, the solutions will not be periodic. And so the way to proceed is to use Chebyshev polynomials. So let's write. So we write our solution, or we approximate our solution as u of n of x. And this is going to be our usual Chebyshev expansion, k of x. K goes from 0 to n minus 1. No big surprises so far. And at this point, the UK delta are the ones that parameterize the solution. If I'm finding the right UK delta, I would be done. But we can also equivalently switch over and take the grid point values to parameterize the solution. So ui are the values u at xi. You can also use those to parameterize the solution. And we can do this because, well, the two are related to each other. We can always get the u tilde from the u's by our S matrix, or we can get the u from the u tilde by using the P matrix. So they're completely equivalent. The nice thing about the U's is that we immediately have one of these UIs being at our boundaries. The very first grid point is at -1, and the very last grid point is at +1. So if we're using the UIs, we have the big advantage that two of the UIs can be immediately used and implied from the boundary conditions. Whereas if we had used the spectral coefficients, well, in order to get the boundary conditions, because the boundary conditions is in real space, the boundary condition would be a much more complicated function of all the spectral coefficients. It can be done, it's not that really big of a deal, but it's just a little bit more convenient using the real space values. And moreover, the nice thing about using the real space values, again on the convenience side, is as soon as you have a solution, you want to plot it. If you use the real space values to begin with, you can just plot them. Otherwise, you would have to do the immense complicated step of converting again with a matrix multiplication. I'm of course joking. Okay, so we have our parametrization. The next step we did on Monday is, and that's the general strategy, is we take our parametrization and we plug it back into our original equation. So we substitute UN into our differential equation, which I'm giving a name up here now. I'm calling this star. And what comes out of there is the quantity that's named residual. Well, it's UN double prime of x minus whatever we have up here, x to the 6 minus 3x squared times UN of x. And because UN is an approximate solution, we cannot expect this to be identically 0, but we still hope to make it as close to 0 as we can. And this was going to go, what's going to give us the conditions to fix our degrees of freedom. Okay, on Monday, I chose at this point 3 semi-random numbers, minus 0.5, 0, and plus 0.5, and evaluated my residual at these 3 values. Now you won't be surprised to guess that we will be using our grid points because the grid points are so nice. So we specialize the grid points xi. And so what we are finding is we have from over here, the second derivative, u double prime I at the grid point. Then we have this next thing, xi to the 6 plus 3xi squared. So this is just a function of x. So we substitute xi instead of x, so that's that. And then we have u at the position x again. And this one is supposed to be 0, and I goes from 0 to n minus 1. So these are now the residual equations evaluated precisely at our n grid points. At this point we have n equations, and we can go back to actually attempting to satisfy them exactly. N equations for n unknowns, that should work out. And now, of course, comes the one magic step that I had in the recap, that the second time derivative here, the second spatial derivative, this one is merely a matrix multiplication. So I can write this one here as d squared ij of uj with a sum over j. I'm getting too lazy to write this thing here. So I'm calling this one f of I. And then the next step here would be a minus f of I xi, and this one is 0. And what this now is a matrix equation for the UI. Let me write this out for you. So we have, in the first term, we have this d squared, which has entries all over. It starts with d0, 0 up here. It has a d n minus 0, n minus 1 in this corner. And it ends with d n minus 1, n minus 1 in the bottom right corner. So it's a matrix with numbers that is multiplied by my u vector, u0 to un minus 1. Next term here, I can also write as a matrix. I'm putting f0, f1 to fn minus 1 on the diagonal. And I can again multiply it with u0 to un minus 1. And this whole thing is 0. So we have now a matrix equation that takes the form of A u equals 0, where at that point the A matrix is our second order differentiation matrix from up here in front. And then we have these extra terms here that turn into this diagonal matrix here, minus diagonal matrix of Fi. So, getting closer. And the reason all of this works so nicely is because we have our nice relationship between derivatives at the collocation point as a matrix multiply of the collocation values itself. That's the whole key that makes everything work. Next, we need to think about boundary conditions. Because we haven't yet put in the boundary conditions into our example. And in fact, as written right now on the right-hand side, this is another nice example. Geoffrey, may I steal your trick? Your cards. Guys, do you have the cards? Let's do a question. So, as written, this equation over here on the very right end of the blackboard, how many solutions do they have? A, none. B, 1. C, 2. D, infinitely many. Oh, we can also put in an E, other. I have a linear set of equations, an n by n matrix A multiplying a vector of n unknowns equals 0. And so the question is, if you now try to solve this set of equations, how many solutions will you find for this thing? And in good old Geoffrey fashion, I'm giving you about a minute time, and I'm spending the minute finding my iPhone to actually measure the time, and then we can ask for the answers. Does anybody else still need one of these nice cards? No. Okay. Do you need more time, or are you getting close to a solution? Let's hold up the cards. Okay, I see a fairly big mix of answers here. So let's continue with step 2 of Geoffrey's strategy. Please talk to a neighbor of yours for a minute or so and convince him or her why you are right, or vice versa. And if you both agree already on what the answer is, make sure you have the right reasons why you think this is the answer. Actually, what is the answer? Okay, so let's come to an end and let's try again what you think the answer is. Please hold up the cards again. So we have more uniformity, and I think the uniformity is between the two different answers that may be the right ones here. And this already illustrates that you shouldn't do these types of questions, even if they seem simple, on the spur of the moment, because the answer actually isn't as simple as it seems. So let's first think about this without the Fs. If you didn't have the Fs floating around here, what the problem would be is you're looking for functions where the second derivative is 0. And there's more than one of them, because all the constants and all the linear and x functions will have 0 second derivative. And so you should be finding without the Fs here that the A matrix has a null space of dimension 2, constants and linear functions, and you should be finding infinitely many solutions. So without the Fs, definitely D would be the right answer. With the Fs, it will depend a lot on whether the F actually manages to kill these two linear and constant functions for you or not. I actually don't know what's the case in this situation. Probably it will. And so probably what will come out of this is that 0, u equals 0, is going to be the only solution. And so the answer is somewhere between B and D, depending on precise properties of what's going on with the Fs. But in any case, we can remove all of this ambiguity by putting in the boundary conditions. So let's work in boundary conditions. Our boundary conditions are that the first u is 1 and the last u is 1. And at that stage, we have two possibilities of how to work this in. We could take the two values we know and directly substitute them in here and then only solve for 2 fewer grid points. And this works very well in this particular case because our boundary conditions map really, really nicely to just a single point, u0 and un-1, to one of our unknowns. However, we can also play a different game, which turns out to be more general. We can take our original equation that we had up there. So here's the d squared minus, let's just put d squared minus f delta ij into one matrix directly. So we can take our original equation where we have d00 minus f0, d is around here, d minus f around the diagonal, and d entries all over the space elsewhere. So we can take this matrix times u equals so far 0. And we can take 2 of our lines in our matrix equation and replace them by our boundary conditions. So we could say, well, we have up here u0 anyway. And so this is the u0 equation. And we can say, let's take all these numbers here out, put a 1 here, and put a 1 on the right-hand side. So now the first line of my equations is actually wrong because the 1 needs to be over here. This is the number that goes with u1. The first line of the equation is u0 plus nothing else equals 1. And this is precisely our boundary condition. And we can play the same game with the last equation, un minus 1. Again, we take out the relevant numbers from our original differential equation matrix, put a 1 into the corner. Now we have 0, 0, 0, 0, 0, 0, 0, un minus 1 equals 1. And that would be the second boundary condition. And now we have this modified equation, which now still has the same form as before, au equals, but now we have a b on the right-hand side, which is non-zero. And that non-zero b on the right-hand side will now give us non-zero solutions for u. And the A matrix is mostly the d squared minus fij, but with a change in the first and the last line. So let me bring this up on the screen, just so we see how this actually looks like in practice. Since I have it on the screen right now, let's talk about this one later. Here's how this looks like now in terms of code. I'm picking a certain resolution n equals 5. I'm calling our magic helper function that gives us all the pieces we need to do Chebyshev spectral methods. And now I'm going to assemble this A matrix here. So I'm starting with A equals D2. Python is weird in that it usually does only references to variables. So I'm really making a copy here of D2 because I'm modifying A and I want to be able to modify A without also modifying D2. So A equals D2 is the first part of my differential operator, this thing over here, the T2 matrix. Then I'm taking care of the F terms, loop over indices from 0 to n, and along the diagonal of the A matrix, I subtract off the F contribution. Now I'm over here in this stage of the game, where I have D squared minus the Fs. And now I need to do the red and the yellow replacements. So I take the first column of A and setting it to 0, except the very first 0, 0 element that is going to be 1. I'm taking the last column of A and also setting it to 0, row, the first row and the last row, except the very bottom right element is going to be set to 1. On the right-hand side, we have all zeros except for our two boundary conditions. So let me start with a vector all zeros and put 0 and 1s into the first and the last numbers. And at that point, we have everything set up to do the matrix inversion. But before we're doing this, let's just print the matrix A and see whether it takes the right form. This is what we have. The first line is the advertised 1, 0, 0, 0, 0. This is going to be the lower boundary condition up here. In the middle are various non-zero numbers of various sizes. This is the combination of the second order differentiation matrix and our F terms. And the bottom line again is all zeros with a 1 at the last term. And this is going to be our second boundary condition down here. And I think you might sense a theme here. If our boundary conditions would have been more complicated, well, then the first and the last line would have been more complicated. We can do that. And otherwise, all the middle lines are the ones that are enforcing the differential equations. And we have a nice setup. In one dimension, solving matrix equations is always so remarkably easy because a 5 by 5 matrix or even a 100 by 100 matrix, if I crank up n to 100 later on, is still small enough that your laptop can do this in a millisecond. So we don't have to worry about how solving our matrix equation in any complicated, fancy, smart way. We can just do lin_alg.invert A applied to B. This line basically is, well, U equals A minus 1 of B. And so what comes out of here is going to be our solution. At the grid points, we have 1, 0.8, 0.8, 0.8, 1. So it's starting at 1, going down, going back up, as you would expect. Please note that it actually satisfies our boundary conditions. The first and the last point are 1. And if I'm plotting this, it looks rather unimpressive. And it looks so unimpressive because I only have 5 grid points here and they're connected by straight lines. To make the plots look nicer, we have to interpolate our 5-point solution to more intermediate points. At some point, I got tired of this, and so I actually wrote a little function here that takes function values u and an output grid x, and it computes the spectral coefficients, and then it sums up all the spectral coefficients. Output equals coefficient times Chebyshev polynomial, cosine of k times arc cosine of x, and then it returns it. So this is a helper function. I'm also asking you to write this on the problem set for this afternoon. This is a helper function that simply makes it more convenient to plot this type of result in a different way. So let's see what we have here. We have a grid of 200 grid points. Here's now my Chebyshev interpolate to the fine grid. And if I do this, then what I find is nothing here. Then what looked to be this rather discontinuous curve is actually a function like this that starts at 1, goes down, goes back up. And at that point, as on Monday, we can compare to the actual solution, which I'm also computing along the line. And the actual solution is the green curve. And you see that we're actually getting really, really close to the green curve. You still remember how close we were on Monday when we did this example the first time? Was it similar? Was it better? Was it worse? Here's the Monday result, where the difference was actually quite a bit worse, about 0.015 difference. And now we have, let me activate the right plot with the difference. And now we have something that is visibly closer in the left plot, and that has differences of only 0.004. Any guess of why this is different from what we did on Monday?
Because of choice of collocation.
Exactly. Let's look at the collocation points. Let me just print the collocation points. The collocation points are -1 and +1, where these are boundary conditions. And then we have -0.7, 0, and +0.7. So the Chebyshev method actually told us that the best possible intermediate values to use are ±0.707, square root of 2 actually, it turns out. And on Monday I started with 0.5, and then somebody here asked, hey, what happens if you move the point to a different point? And we guessed 0.7, and the 0.7 we guessed was actually remarkably close to the optimal choice of 0.707. So all of this works. We have reproduced what we did on Monday. But the cool thing now is we've not only reproduced it, we have reproduced it with a first line here that set n equals 5. And now, of course, I'm free to change this n equal 5 around to other values and see whether we get more accurate solutions or not. So this is what this last piece here does, is I'm going from 5 to 9 to 13 to 17. And then in here, I have the identical code we had above, where we are setting up the matrices, and we're setting up the boundary conditions, and we're modifying the matrix for the boundary condition, and we call a to the -1b on it. And let me just execute this. And what comes out of here on the left-hand side are solutions with the 5 grid points that we had on the previous plot. And 9, 13, 17 are all on top of each other, and they are all on top of the 2 solution within the line thickness. So in order to appreciate how accurate this actually is, oh, something is here on the way. That's not me, it's the main Zoom panel. To appreciate how accurate this actually is, it doesn't really matter because the plot just keeps on going to the right the same way. You have to plot differences. So here is the difference 5 minus 9. That's the blue line. And if we assume that 9 is a lot more accurate than 5, the 5 minus 9 is going to tell us that the 5 solution is good to about 10 to the minus 2. 9 minus 13 tells us that the 9 solution is good to about 10 to the minus 4. And the U13 is good to about 10 to the minus 6 or so. And so with only 13 basis functions inverting a 13 by 13 matrix, we have solved this differential equation over here to 6 significant digits. Not bad for a few lines of work. Of course, you can also go further if you like. And then On the left-hand side, nothing else changes because everything is already within the line thickness. On the right-hand side, these curves keep on going further down until ultimately they level off because we are running again into the truncation error 10 to the minus 16 difficulties of floating point numbers on a computer. You might wonder why we are not at 10 to the minus 13 here, but 10 to the minus 16, but more like 10 to the minus 13. And the difficulty comes about because of the derivatives. It turns out if you take a derivative of a Chebyshev polynomial, what you get back is of order k squared. So if you want to take second derivatives, you get back order k to the fourth. And this number k to the fourth, if I'm having, what do I have here, 25 points, well, 25 to the 4, well, this is already a few orders of magnitudes. And this is what causes the error to be magnified from 10 to the minus 16 to 10 to the minus 13. It's just that the derivatives are increasing the size of numbers, and that takes away from the available dynamic range of floating point numbers. Okay. So down here, this is asymmetric because it's a very good question. So once you are in floating point truncation error regimes, all weird things do happen. For instance, the result you get will depend in which order numbers are being summed up. And if you sum up from left to right, then perhaps, well, on the left you get bigger values than on the right. It's not unusual that floating point truncation error, round-off error is the right word, actually destroys any symmetries you might have. Okay, I am running as always slow. Yes?
So in the original equation, the second term was multiplied with the polynomial, which is of order 6. So this order does not have anything to do with the approximation order in terms of Chebyshev polynomial.
That's an excellent question. So if we multiply here by a different polynomial, then this term can leak out to higher order in X than what we are representing. So if you take the n minus Tn minus 1 here, then you have n minus 1 plus 6. You have a polynomial, this is a power of x to the 6 higher than what we started out with and what we can represent. This introduces an error in the scheme because these high powers that should be represented by Chebyshev polynomials that we don't have, those will be folded back into some of the existing Chebyshev polynomials and will cause errors in these spectral coefficients. What helps here is that the spectral coefficients we would have needed to keep everything correct are exponentially small. And so as we increase n, the coefficients we don't have, which we would have needed, become ever smaller, and therefore the error we are making becomes ever smaller. This effect of taking higher order modes that are not representable on the grid being reflected back into the grid is called aliasing. And one can do fancy things like keeping extra modes around to guard against aliasing. Or one can do what I'm doing here, just not worry about it, because the aliasing is proportional to the modes we are not representing. And since those are exponentially small, increasing n a little bit makes them also a lot smaller and nothing to worry about. And curiously enough, even with 5 modes, where we have a x to the 5th here and an x to the 11th floating around here, even with 5 modes, this hardly mattered because the error is only 0.1%. Okay. So if you now want to do other boundary conditions, this would be done by, well, ending up with different numbers in your boundary condition line up here. And the refinement of this problem that I'm asking you as well to do this afternoon is to resolve this problem where one of the boundary conditions is a von Neumann condition. And if you now expand this du dx equals 0, well, you can write this as differentiation matrices. And if you want to do this at x equals 1, well, actually, let's take x equals, let's take x equals 1, doesn't really matter. Then what this means is that this equation is going to hold for I equals n minus 1. And so what this means is that for in the x equal 1 boundary condition, you would end up with the entries d n minus 1 comma j going along here. And so by putting these, the values of the differentiation matrix here, the last line now becomes differentiation matrix times the u's, which is exactly the derivative at x equals 1. And if you want this to be 0, well, you need a 0 on the right-hand side. And now with this modification, I would be solving the same problem with von Neumann boundary condition on one of the two sides. Because it's only on one of the two sides, the problem will finally also become non-symmetric. And so we are finally having something that is more interesting than just a little dot. I don't want to go into more detail here because I still need to play the very same game for you for eigenvalue equations. And since I'm running quite late, I have to speed up a little bit. Otherwise, you will have difficulty with the problem set this afternoon. So let me switch back to eigenvalue equations. The equations we had was a u double prime equals minus omega squared u of x. And x was from minus 1 to 1. And we had boundary conditions that at both ends u is going to be 0. So usually when you have eigenvalue problems, you have one number lambda here, and this is the eigenvalue. But if we have minus omega squared in the problem, well, this just means that once we get back lambda, we then have to solve for the omega, but that's not a difficult step. Okay, so now let's discretize again. And we're doing exactly the same that we did over here. The u double prime turns at a u double prime at the I, at the grid points. So we discretize at grid points. The u double I turns into a d squared ij uj sum I. And the right-hand side is a minus omega squared ui. And so what we have is basically an equation d squared times u equals lambda times u. And this is already an eigenvalue matrix problem. I assume you know what these words mean. where we now want to solve at the same time for the vector u and for the real number lambda. We need to think about boundary conditions again. This doesn't go away because in this form, this won't work just yet. We haven't worked in the boundary conditions. So working in the boundary conditions is unfortunately a little bit more complicated than before. So let me spell out the matrix here for you. So we have D00, D0 n minus 1, D n minus 1, 0, D n minus 1, n minus 1. And all of these are D squares. Then we have our U0 to UN minus 1 equals lambda U0 to UN minus 1. So what we did beforehand is we took the first and the last line here and replaced it by our boundary condition. And the fact that made it work is that we also had the one on the right-hand side. Now, however, the difficulty we are running into now, if I'm taking the first line here and replacing them by all zeros, because my boundary condition is 0, well, I want a 1 over here, then yes, I can do this on the left-hand side, but I don't have control over this term over here because that term is given by the definition of what an eigenvalue problem is and what the eigenvalue routines are doing. I can't modify this one here. And so the first line would correspond to an equation like U0 equals lambda times U0. And well, 0 is a solution of this one, but if lambda happens to be 0, then there could be spurious other solutions. And so this is not a good situation to be in. The solution that I'm recommending you doing is literally taking out the full first line from left to right. And if we don't have the U0, because it was 0, that means that all multiplications with U0 over here go into the first line. So the first line and the last line are also taken away. And what remains then as our A matrix is the stuff in the middle. So A here is a n minus 2 times n minus 2 matrix. And what this now boils down in practice is the following sequence of steps. We compute the second order differentiation matrix with our usual Chebyshev helper as usual. And then we set our A matrix to be D2, well, from the first row to the one part the end, from the first column to one part the end. And then we can call our NumPy routine npy.linalg.ig of A. And this is going to return to us the eigenvalues and the eigenvectors. And so it will return n minus 2 of those, because we now have an n minus 2 by n minus 2 matrix. And those eigenvectors and eigenvalues should more or less correspond to the first n minus 2 eigenvalues and eigenvectors of the original non-discretized equation of this one here that we started out with. At that point, there's still, unfortunately, a remarkably long list of things that can go wrong. The most important thing that goes wrong is that the eigenvalues you get back, or a certain eigenvalue you get back, will only be as accurate as the corresponding eigenvector. If the eigenfunction is wrong because of discretization error, then the eigenvector, eigenvalue, will also be wrong. Why does this matter here? So it turns out, if you look at eigenvalue problems, you typically get a sequence of eigenvectors, of eigenvalues. So you get a lambda goes from small to ever larger. And the corresponding eigenvalues tend to be long wavelength solution. And each higher order one tends to have a finer and finer structure. For our oscillating string, you really get back sine waves of ever increasing period, ever shortening period. And ultimately, if you're up to n minus 2, you will have a lot of these periods. And this cannot be well represented on our Chebyshev grid because it has too fine structure. So what's going to happen is that the low eigenvalues, the ones we most care about, the fundamental modes and the first overtones, those are associated with long wavelength solutions, which can be well represented. And so the solution and the eigenvalue will be accurate. But as you go to the high end, the eigenvalues and the eigenvectors, the solutions, will be entirely off. So to fix this, you will, unfortunately, the only thing that really works is to solve with different n, and then check how many of the low eigenvalues are indeed the same between solutions at different resolutions. There's more things that can go wrong. Oh, shoot. I apologize for anybody online. I hope you didn't just see my screen sharing, but you still saw the blackboard the last 10 minutes because that was important. There's more things that can go wrong. And let me just briefly bring up the problem set because I don't have the time to write this on the blackboard. More things that are going to go wrong, I am listing here in a long list behind. So let's see, task D, discretize the eigenvalue problem with the Chebyshev series. Solve the problem at different n and check which eigenvalues are identical between different resolutions. Those are the ones you can trust. Good. Yes? I'm not screen sharing. Okay. Thank you for telling me. This is, of course, important. Step 1. Solve at different n and find which ones you can trust. For resolutions high enough that you can trust the eigenvalue, plot the corresponding eigenfunctions. So what should come out of here are these sine waves. But now, unfortunately, comes the long list of stupidity that has to do with numpy.lin.alg. So, the difficulty is, well, you're getting returned n-2 eigenvalues and eigenvectors, but before you can actually make nice plots with them, there's a lot of work you have to do. Number one, the sheer stupid format in which the eigenvectors are returned, I find awkward to work with. So I would suggest you rearrange whatever is coming back here into a list, such that you can actually write evec of I to get the ith eigenvector. Then, eigenvectors have the unfortunate property that their overall magnitude, their scaling, is undetermined. You can rescale it as you wish, and you still get an eigenvector. This has two difficulties. Number one, there could be an overall sign flip that a function is returned is not this one here, but it's this one. And so you need to flip the sign to make them all look similar and not sometimes plus and minus of each other. You also need to put back the zeros and the last value because we've cut them away, and so linalg.ig doesn't know about it, and it can't return the points it doesn't know about. And you also need to rescale them such that they have the same amplitude for different resolutions. The next difficulty that comes up is that you get back eigenvalues and eigenvectors, but they come back in an arbitrary ordering. So you actually have to sort them from small to large. Otherwise, you don't know which ones to compare between different resolutions. And this whole post-processing business has been difficult enough when I was trying to do this problem myself that I ended up writing a separate function, solve oscillating string, that has two lines. I can just show you. I have the power here to show you things, haha. That has two lines. Where am I? Yes, I think this is right. Exercises 2. The solve oscillating string, wherever it is. Here it is. It has a whole 3 lines to do the math. It sets up the problem in line 35. It solves it in line 36. So far, so good. And now let me just go down to show you what the quickest solution is I found to get everything post-processed in a nice way. Sorry. At the end, however, we have omegas sorted by size, and we have the eigenvectors in a nice ordered list. And then we can play this game at different resolutions, and we always have the omegas and the eigenvectors and can make nice plots thereafter, like this one's here. So ultimately, it will work, but unfortunately, getting there requires all these extra post-processing steps that because of dealing with the eigenvalue routines in linear algebra. Okay, I apologize for running over time for a few minutes, but I wanted to get through the eigenvalues enough that you can actually have a fighting chance this afternoon. And I wish you a lot of fun this afternoon, and I'm either meeting you in the hallway and chatting with you, or otherwise tomorrow again. Thank you very much.